Okay, so this time around, we want to look at differentiation of implicit functions. Now, first thing you want to do is understand what an implicit function is, so that we can see how we differentiate such. So there are two types of functions in this category, or for you to understand what this one is. So we have explicit, and then the other one. So we have an explicit function, while the other is an implicit function. So we rarely use the term, or it's rarely singled out to say explicit, because I think it's just an oversight. It's understood to say that you know what it means. But to write a function explicitly, okay, someone trying to join. To present a function in an explicit way means if you have a function that shows the relationship between x and y, so we can write y as an explicit function of x. So if you can make y the subject of the formula and write it in terms of x, then we have written this explicitly. We have written y explicitly as a function of x. So if it is possible for you to make y the subject of the formula, then such a function will be taken as an explicit function. But so of course, good examples of such functions would be if you have y is equal to x squared plus 2xy. Basically, all the expressions we've been looking at so far, they have been explicit functions. Take this one, for example. Say you wanted to find dy dx for this function. If you wanted to treat it as an explicit function, it means that you don't want to go directly to differentiate y because of this y, which is this side. Instead, you want to write it as an explicit function. Doing so means making y the subject of the formula, writing it or presenting it as a function of x. First, I have moved this to the left, and then now I'll factor out y. I'll remain with this is equals to x squared. And then lastly, I'll now write y as the subject of the formula. And this would be 1 minus 2x. Notice that now we have presented y as a function of x. So this is an example of an explicit function. So here, it was possible for us to make y the subject of the formula. After making y the subject of the formula, notice that now you can obtain the derivative of y with respect to x, and seeing the way it looks, you might want to say that, okay, I'll differentiate this. Do you guys remember what method did you use to differentiate here?
Quotient.
Yes, quotient rule will work best here because we are seeing that division taking place. So I'm going to use quotient rule here, and it's going to work very well, and you're going to get your derivative. But every now and then you will find expressions for which you cannot make y the subject of the formula. You cannot write it explicitly. How do you approach such? Take, for example, you have something like, let's say, 3x squared plus y squared minus 5x. And then to just weird it up, you also have a y there is equals to 2. Here, you can try all you want to make y the subject of the formula. And you realize that it might be possible, but it's just not so straightforward. It's not easy to do that. If you try this, maybe complete the square here and there, then square root, it's just going to become messy. So for such functions, especially you have, maybe sometimes you have even y is equal to sine, and then you have xy. So something like this. Again, this is an impossible situation or a difficult situation where making y the subject of the formula will be tricky. Here you have y, which is an argument of a sine there. So this is going to be rather difficult to handle. Another one I can present is, let's say you have 4x squared plus 2x. Then here you have y to the power 3. And then you have 5y squared is equals to 0. So if we wanted to find the derivative here, again, if you wanted to treat it as an explicit function, you'd have to make y the subject of the formula if your goal is to get dy dx. But when you look at it, how on earth are you going to isolate y, seeing that here it's y to the power 3, here it's y to the power 2? It is going to be very difficult. So for such cases, we're saying, hey, we understand that we can't make y the subject of the formula. But is it possible to differentiate? Yes, it is. All we want to know or to keep in mind is y is indeed a function of x. It's possible. Y is a function of x, but we just can't present it in that way. So when differentiating y, or when differentiating this expression, we're now just going to differentiate it implicitly, meaning we will differentiate it as it is without making y the subject of the formula. We know to say, okay, y somehow is a function of x, but we have no idea how to represent it in such a way. So we'll say, we'll differentiate the expression exactly the way it is, but just keeping in mind that y is not just any variable. It is a variable that depends on x. So the method we are going to deploy to differentiate such expressions, it is basically chain rule. But how did chain rule work? If you recall, for chain rule, we said, okay, let's say you have a simple function here, x squared minus 3, and then raised to the power 5. When we were just introducing chain rule, remember we ended up concluding that the derivative of dy dx was equal to differentiate this just by looking at the power. So get the power, multiply it down here, keep the function the way it is. Then the next step was multiply this by the derivative of what is inside here. So in this case, it would be the derivative of x squared minus 3, which would just be 2x. So here, by chain rule, the answer ends up being 10x, then x squared minus 3. This is a way of dealing with chain rule that we ended up with. But in its strict sense, you might have something like x squared minus 3 raised to the power. I have 5 as the power. Did I reduce the power? Oh, yeah. This is a 4 here because the power reduces by 1. I hope you guys followed that. That's a 4 here. Okay. So if we now wanted to use chain rule, how does it work? Basically, it's exactly what I'm from doing earlier, but I'm just going to add an in-between step here. Let u be equal to the argument of that power, which is x squared minus 3. So here, this is a classic example where we're saying, we know that we're defining u, but u is a function of x. U does depend on x. So to differentiate y, because now the expression has changed to y is equals to, instead of this, we now have u to the power 5. But we know that u depends on x. So to differentiate y now with respect to x, what do you do? If you recall how we used chain rule, first differentiate y with respect to u. Then multiply this by the derivative of u now with respect to x. If you think about it, this is exactly what we did here. U is this argument, what is inside here. So first, differentiate y with respect to u, meaning just basically focusing on the power. The power multiplies here, and then it reduces by 1, and then multiply it by what? The derivative of u, meaning the derivative of the argument of that term in the brackets. So this is basically the derivative of u. So if we bring that back, dy du, this is now what you're differentiating, which gives you 5u. And then this becomes to the power 4. But then multiply this by the derivative of u with respect to x. In implicit differentiation, this is exactly what will be happening. But the only difference is we will not be evaluating this derivative of u with respect to x. For this case, we know what u is. U is x squared minus 3, so you can differentiate it. But for implicit functions, we have no clue what u is. So we will not be able to get du dx, so we will leave it the way it is. Let me give you an example. Let's pick the first function we isolated or we selected. Let's get this one. Say we wanted to differentiate this implicitly, or we can actually get, okay, this one, I brought it here. I didn't go all the way to solving it, so I'll leave it like that. I wanted to just use that so that we differentiate it also implicitly. Say I wanted to get the derivative of this function implicitly. So it means that just keep in mind that y does depend on x, but we just don't know how to present it in that way. So think of y as if it is our u in this expression. Think about it as if that's what you have. But now how do you differentiate it? Differentiate the entire expression with respect to x. So first, you come to the first term. Differentiate the first term with respect to x. So this one will just differentiate in a normal way. The 2 comes down to multiply the 3, giving you 6. The power for the 2 reduced for the x here reduces by 1 to become just 1. But problems will arise where you have the y squared. Now, having presented on implicit differentiation a number of times, I'll give you an approach which seems to work for most students. You can try to understand the chain rule, that method that I was describing here, but you can also just use one simple trick. When you find y, while differentiating implicitly, when you find y, just differentiate it normal as if it were an x first. So what do you do? The 2 multiplies down, or the power of the y multiplies down, so it becomes 2 multiplying y. Then the power reduces by 1. So the power here is 2, reduces by 1, the power becomes 1. But every time when you're differentiating y, always multiply it by dy dx. So this is one simple trick that you can use. And if you think about it, this is chain rule, because in a way, it's this. First, differentiate y with its power. This is the part where the 2 multiplied down and then the 2 reduced by 1. But then multiply it by what? Du dx. For our current case, you're multiplying with dy dx. So let's see, we'll see it happen there again. This will be minus, this is 5x. Here you're differentiating, this is an x, doesn't have a y, so we're differentiating it in the normal way. The derivative of 5x would just be 5. Don't forget the negative, it just comes straight there, it won't be changed. Now we see y. So what is the derivative of y? This is y to the power 1. So again, if it were x to the power 1, when you differentiate it, the answer would have been 1. So again, differentiate it as if it is just x. So since this is y to the power 1, when you differentiate it, the answer is 1. But remember what I said here? Every time when you differentiate y, what happens? You have to multiply by dy dx. All in all, because this is a 1, it's as if this will just remain as dy dx. So if you're differentiating y on its own without, maybe the power is 1, then the answer will be dy dx. Lastly, the right-hand side, it's a constant, that's a 2. So it doesn't change. The derivative of a constant will be 0. This is implicit differentiation. What is left here is just to simplify this. But before we go to simplification, do we have a question? Okay, looks like we are fine so far. Once you're done with differentiating the first round, so we're basically done, but now we just want to get our answer. Don't forget the 1 here, this is not a prime, because a prime would mean we're differentiating there, but this is just that was for the power. So let me just remove it because we know it's as good as not having it there. So now what you have to do is Get all the terms which contain dy dx. Isolate them on the left-hand side of the equation. And all the other terms without the dy dx must go on the right. So now you have 2y dy dx, then plus dy dx. On the right, the 5 becomes positive, and then the 6x becomes negative. For the terms on the left side, I'll factor out dy dx. So I'll remove this, and I'll remove this. So if I factored out dy dx, what remains? For the first term, only this will remain, 2y. For the second term, only a 1 will remain there. And then on the right, we still have 5 minus 6x. So that now the final answer will be this is equal to 5 minus 6x over 2y plus 1. So this becomes the derivative after differentiating implicitly. Do you have a question there? Let's look at another. For this one, I want something that we can actually check. We'll pick an example which we can differentiate implicitly, and we can also differentiate explicitly. So I'll pick the equation of a circle. So let's say a circle of radius 2, something like this. So we want to find dy dx. Clearly, for something like this, you should understand that it is possible to get to write y as a function of x. It's possible. Let's start with that form. So if we wanted to do it explicitly, how would we do it? We want to make y the subject of the formula. So first, I'll leave y squared on left. X squared goes on the right. And then now square root, so that now we have 4 minus x squared, and then the square root like this. Now, I just wanted to mention that here, this is not the same as the square root of 4 minus the square root of x squared. I've seen students tend to make this mistake here. The two are not the same. So because of that, we'll leave it the way it is. But to differentiate this, it will be important for us to write the square root as a power. So this is going to be, do you know the power? Want to place what as a power? Do you remember?
Half.
Yes. So this will be raised to the power half. So now we can differentiate. And the method of differentiation we're going to use here, do you remember it? So we'll be using the method we are describing earlier on, chain rule. So how does it go? First, I'll multiply the power down. I'll keep what is in the brackets the way it is. I'll reduce the power by 1. Then I'll multiply this by the derivative of what is inside. The derivative of 4 is 0. Now, don't forget there's a minus showing up there. So the derivative of minus x squared. So it will be minus here, but the 2 will multiply it down, x, and the power of the x will reduce by 1, so that it will just be like that. So this becomes the derivative. Now I'll just simplify this. The half here and the 2 here will cancel. So that now I have just negative x from this one here. And then here I still have 4 minus x squared. But the power that is half minus 1, this will remain as minus half. Next, the power is now negative. Remember, if you have x to the power negative any power, any number, negative n, you should recall that this is the same as 1 over the same thing, but just with a positive power this time. So this is going to be 1 over x. to the power, the same power there. So just to remind you on that. So with that in mind, yes, please.
We'll just go back a little on, how you simplified the 4 minus x squared in the brackets.
Oh, okay. So the term was differentiating this one, right?
Yes.
Okay. So what was happening there is we had this. So how we differentiate? First, multiply the power down. Keep what is here the way it is. Then the power reduces by 1. Then multiply the whole thing. Now differentiate what is inside. So now we're just differentiating 4 minus x squared. First, differentiate 4. That will be 0. Then the sign on the middle is a minus. Now differentiate x squared. The 2 comes down, the x comes here, then reduce the power of the x by 1. The first part will remain 1 over 2, and then 4 minus x squared. Half minus 1 is minus half. But now this is a 0, so no need to write it. But now this will be minus 2x. This is 2 minus 1, which will just be 1. So it will remain like this. Now I'll multiply this with this, because these two can multiply. So that on top I'll have negative 2x, which is just this, but divided by 2, which is this 2 here. And then I still have the 4 minus x squared to the power minus half. The 2 and the 2 now cancel, leaving me with minus x, and then 4 minus x squared to the power minus half. Are we okay?
Yes, we are. Just write it down.
Okay. So from here now, so this is where now I was saying that we can recall that if you have x raised to a negative power, now I was generalizing to just say that the power is n, some real power. Even if it's not real, it still applies. So this will be equal to 1 over the same variable x, the same power n. Now it will be positive. When it is up, it is negative. Comes down, it will be positive. Vice versa works as well. If I have n raised, not n, if I have x raised to a positive power n, I can write this as 1 over x raised to a negative power n. So this is still fine. But mostly we take advantage of the other one. So taking advantage of that same property, it now implies that this thing here, I can use that property and say 1 over, now it will be 4 minus x. This is squared, x squared. But now the power was negative half, the power is now positive half. Then remember again that if you have x raised to power half, this is the same as the square root of x. Using this, we now see that this is negative x multiplying. This is now 1 over, where we have this because of that positive half as a power. It's now the same as the square root of 4 minus x squared. So that finally, this is negative x over root 4 minus x squared. This becomes the final answer. So here, this is after differentiating explicitly. Now the question is, can we find the same answer after differentiating the same expression, but now implicitly? Again, implicitly just means without trying to make y the subject of the formula, just differentiating things the way they are. Is it possible? Let's try. X squared plus y squared. This was equals to 4. Now, for explicit, you saw how long it took and what we had to do. We started solving this somewhere here. We had to make y subject. We square rooted here and there. We had to differentiate. We saw how long it took. But let's try the other method. For the other method, all we do right here, we'll start differentiating. When differentiating x, it's business as usual. 2 multiplies down, the power of x reduces by 1, we have 2x. Now we have y, where complications arise. When differentiating y, remember what I said? Take it as if it is x as well. How do you differentiate? 2 multiplies down, and then the variable remains here. The power of the variable reduces by 1, so it will just be y to the power 1. But because this is y, every time you differentiate y, you must multiply it with dy dx. So we have this. Then equal to, on the right side, we have a constant. Nothing changes. The derivative of a constant is a 0. So we have this. Now what follows? Isolate. The terms with the dy dx must remain on the left side. The terms without must go on the right. Now we have 2y dy dx equals to negative 2x. At this point, you see that the 2 and the 2 will divide out. So now we have y dy dx is equal to negative x. See what is left? Just divide both sides by y. So now we just have to divide both sides by y. So that dy dx is equal to negative x over y. At this point, we are done. But are the solutions the same? So 2 questions for you guys. Are the solutions the same? Question 1. Implicit, we found this. Explicit, we found this. Are they the same?
They don't look to be.
Okay. But which method is better? Which method is shorter and faster?
Implicit.
Implicit is faster. Now, in as much as they might not seem to be the same, they are actually the same. Notice one thing here. If I just went back to this expression and made y subject of the formula, here we can see that it's possible to make y subject of the formula. See what we end up with. And now if I was to get y and plug it where y is, don't you see that now we have the exact expression we got using explicit?
Sorry, come again. Yeah.
Okay. We had 2 expressions. From explicit, we had this at the final solution. But from implicit, the final solution had this form. Now, implicit, in most cases, we use it in situations where it's not easy to make y subject of the formula. But if it were possible, you can put y here, or whatever y is equal to there, and it will still be the same. Now, what I said was, even though they might seem as if they are different, the 2 expressions are actually the same. To convince you that they are the same, here our example was one where it was even possible to make y the subject of the formula. So I said, okay, since we can, let's find the equivalency of what y is. So we made y subject of the formula. We had this, and this was there. And we saw that we ended up with y being equals to the square root of 4 minus x squared. So that now, if we were to put where there's y, if we were to put its equivalency, notice that now we get the two expressions to be exactly the same. So we conclude that whether we do it implicitly or explicitly, we get the same answer. But the only thing is, not all equations will have the two methods working. For some questions, as you'll see in the next examples, it will be very difficult for us to do it explicitly. So for such, we will have to stick with implicit, because for such, if we can't make y the subject, then we have to differentiate it the way it is, implicitly. Have you got it now? Are we okay?
Yes.
Okay. So I picked that example to just show you that implicitly, explicitly, they both work, but explicitly will have a limit to when it can work. But explicitly, we'll be able to save you, and in most cases, it will shorten. Let's get another example so that you guys have a broader understanding of how implicit works. This is a nice one. The previous two examples were okay, but they did not involve too many rough steps. What will give us a rough step here will be this part here. So let's see. We want to do it implicitly. So we'll just go right ahead here, and we want to differentiate this with respect to x. The question says find dy dx. So differentiating the first step straightforward. That will just be 2 multiplies down, we get 8. Then x here, the power 4, the x there reduces by 1. So just leave it as 8x. But trouble will be here. Because how are we going to differentiate that term? What you have to see here is, unlike the previous examples, here you have two parts. X is present and y is present. Now, this is not one term. Instead, we can see it as two terms, or rather, two functions. So to differentiate this, we have to do it by product rule, because we have the x function, and then the other function comes with the y. So we're going to differentiate this by product rule. So we're going to have plus. How does product rule work? So first, you know how product rule works? You don't have to be strict on which one you start by differentiating. Just pick one. So for the first part, I will keep y to the power 3 constant. So I'll hold it. I'll differentiate 2x. So when I differentiate 2x, I will get just 2. So this will be times 2. Then plus. What I differentiated on the first one was 2x. So now it is the one I will not differentiate, 2x. But now I have to differentiate the other, meaning now I am differentiating y to the power 3. The derivative of y to the power 3 will be 3 comes down, then y, the power for y reduces by 1, so it becomes power 2. But remember, whenever you differentiate y, what do you do? Do you remember?
Multiply, divide.
Yes, whenever you handle y, you must remember to multiply by dy dx. There. After doing this, you are now done with product rule for such an expression. This is what made this problem a little bit different to the previous one, because it now had product rule mixed up with implicit differentiation. But when we proceed to the next one, it's 5y squared. So again, 2 multiplies the 5 to give you 10. The power for the y reduces by 1. And just like before, it's y differentiating dy dx. Then equals to 0. The only thing left is now to simplify this, make dy dx subject, then we're done. So I'll sort out the brackets. This will be 2y to the power 3 plus, so 2 and 3 will give us a 6, y to the power 2, then dy dx minus 10y dy dx. Then this is equals to 0. Hope I haven't made any silly errors anywhere here. So from at this point, remember what we go to next. All the terms that have dy dx must be isolated on the left side. Everything without must go to the right. So on the right, we now have negative 8x negative 2y to the power 3. Okay. So next up, factor out dy dx from the terms on the left. And we see that we have dy dx here. This will be 6xy squared minus 10y. On the right, this will still be the same. Okay, so once that is done, now divide both sides by this part here, so that finally our dy dx will be equal to minus 8x minus 2y to the power 3 divided by 6x y squared minus 10y. Few things, we see that this can simplify a little bit. 2 can divide into everything. But I also don't like the fact that the terms here are negative, negative. When down we have a positive and a negative. We can sort out this because we really don't like negative starting here. So we always want to hide it. So instead of dividing by just 2, I'll divide by negative 2. What that will do is, the first term divided by negative 1 is every term will be divided by negative 2. So that in the end, like I'm multiplying by negative half on top and also multiplying by negative half down. So that in the end, I'm basically multiplying by 1. So I'm not changing the expression. The first term becomes positive. 8 divided by 2 will give us 4x. The second term also becomes positive, but 2 divided by 2 will be 1. This will remain as just y to the power 3. In the denominator, you see that the 6 will be divided by 2 to give 3, but the negative will make the 6 to be negative. So I'll end with the 6, but when it's divided by 2, it will reduce to 3. When the same thing happens to the 10y, the negative will make it positive, halving it to give a 5, and then this will be y. So this is what we're going to have. And this will be the final expression. You can leave it at this stage. It's okay, but by presentation, this is preferred. Okay, so this becomes the final answer. Any questions so far? Okay, so this looks like it is fine. The next thing we want to look at, it's about higher order derivatives. Now, especially when it's about implicit functions. I think that's where I've come to think that's where you're likely to find a little bit of trouble. But let's start with the more basic ones. So when it comes to higher order derivatives, We're just trying to say the second derivative, third derivative, fourth derivative. So what does it mean? You differentiate a function once, then you differentiate it again. The same function, differentiate it the first time, gives you one thing, differentiate it again. So like you have y is equals to x to the power n. When you get its first derivative, so I'll use prime now. We did discuss a prime here can also be used to mean dy dx. So when you differentiate this the first time, n comes down, and then it will multiply x. What happens to the power? It reduces by 1. When you differentiate it again the second time, now you have y double prime. So this will be written as d like this with the y. And then you have dy, dx, I mean, and then the 2 will be here. So take note of the notation here. We're trying to avoid, what you're trying to avoid here is writing it as d this over d this. This will seem as if it will just cancel out and then reduces to nothing. Not necessarily that. We don't do this. This will seem as if it will go out like that. But instead, what you do is the 2 here will be positioned this side. Then one other thing here is when writing the second derivative, you might think, because basically it's the same thing that you differentiated once. Now you want to differentiate it the second time, like that. So I want to differentiate it the second time. Now, we do not write it as this. We don't write it like this. Again, let's see that this will seem as if it is going to go away. But instead, I'm emphasizing that we must write it the first one, the one on top, the square on the middle, the one down, the square is that side. So this is the second derivative. So it goes on to the third derivative, the fourth derivative, and so on. But all in all, I want to say the double prime here means this, which is basically just the derivative of the first derivative we obtained. So this is what we are looking at. So in other words, if y prime was this, if the first derivative was that, we now want to differentiate the first derivative. So we want to differentiate the first derivative. So we want to differentiate it. So what do we get? So again, we treat it as if we're starting from here. We want to differentiate it. And the power again multiplies down. We already had an n here, but now that new power will multiply here, n minus 1. And then what happens? The power reduces by 1. So I have n minus 1, the one which was already there. Now we'll reduce it by 1, which becomes n minus 2. The third derivative, y triple prime. Again, we already have this because we're differentiating the second derivative. That's what we're differentiating. So we already have n minus 2. So this becomes as n minus 1. So this is what we already had, but now we'll multiply it by that power. So this will be n minus 2. And then x, what do we do? Now the power reduces by 1 again. So this becomes minus 3. So this is how we get higher order derivatives. It's the same that we keep differentiating. Let me give you an example, since that was just a general case. By the way, all the methods of differentiation we have looked at so far can be used to differentiate these expressions. So even quotient rule is fair game here. Even product rule is okay. So we won't only be dealing with powers. But for starters, we have the simple ones. Let's say you have the square root of x. Maybe not so simple. Square root of x. The first derivative, dy dx, what do we have? We know to say we can write this as power half. So this becomes 1 over 2 multiplying down here, and then this will be to the power minus half when we reduce the power by 1. This is okay, we can leave it here, but we know to say this can be written as 1 over 2, and then this is now 1 over the square root of x. So maybe I should first say 1 over x to the power half. That is after sorting out that negative power. And finally, this is what will become 1 over 2, and then root x. So somewhere there. Now, let's get the second derivative. The second derivative, I'll choose to view it from here. I'll not look at it from there. It might, because even if I had this expression, I'll first want to present it in this way so that I can easily differentiate it. So this is what I'll be differentiating. Above all, it's the first derivative. So in differentiating, what I'm doing, power multiplies down, so that power is negative half. But what is it multiplying? Already you still had the half which was down here, this one, and then you have the x here. Then what happens? The power reduces by 1. So you had negative half. Now you need to reduce it by 1. So this is what we're going to have there. Reducing this by 1, what does it imply? Now we're going to have negative half times half will give us 1 over 4. This will be x. When we subtract here, this will end up being negative 3 over 2. That becomes the power. Of course, we can try to write this in a simplified version. This will be minus 1 over 4, and this will be 1 over x to the power 3 over 2. What does this imply? This is the same as negative 1 over 4. Then we have the root here. This is not looking too good. So you have 1, I wanted to write it as 1 over, we have 4 here, then we have the root. Now you know how it goes. The 2 comes here, and then x raised to the power 3, like this. So of course, this being a 2, we can even skip it out, it's still fine. So this becomes the expression. From there, we can even get the third derivative. But for the third derivative, again, when differentiating, I will always prefer to differentiate this version of it. Remember, this is the same as this, but differentiating it from here will be weird. So even if I was given this, I'll first take it to this form, then from this form, I'll take it to this form. This is its version that I will differentiate. So when I differentiate it there, again, the power multiplies down, meaning I'll have minus 3 over 2. What is it multiplying? We already had the minus half there. And then x raised to the power, we have minus 3 over 2, but we need to subtract 1. So I hope you're seeing how these higher order derivatives are going. But it's not always this simple. A classic example of how this can become not so simple is when we're dealing with explicit functions. A good one is this one. Now, is that? A good one is this expression. So previously, we saw that for this one, we already obtained its derivative implicitly and also explicitly. So we now want to get the first derivative and the second derivative. So for the first derivative, we already saw it. So we did implicit, and then this is what we ended up with. But now we want to go a step further and get the second derivative. Now, the first derivative, we can even get this version since we are still going. Now we want to get the second derivative. What will be the second derivative? Now, where you pick it up from, completely up to you. You can choose to pick it up from here, but notice that if you pick it from here, then you have to differentiate in the right-hand side. It will implicitly or partially by quotient rule. But usually I try to avoid quotient rule when I'm doing this because it's not really a pleasant approach. So I just take it a step before the division, so that at least I will be dealing with product rule. I tend to favor product rule over quotient rule. But again, depending with which one you're comfortable with. So in getting the second derivative, I'll choose to differentiate it while it is in this form. So this is when I'll differentiate it again. So notice that here you have two terms. This is one and this is the other. So you have two functions. So in differentiating that part, I'll say, again, completely up to you, I'll say I'll keep my dy dx constant. And I'll differentiate y. So when I differentiate y, I'm basically saying the derivative of y is 1. Then I'll multiply by dy dx. That's everything on the left side. How about on the right? That's not everything. I'm using product rule. Remember, I almost skipped that part. Here, I kept dy dx constant. I differentiated y. Now, I will keep y, and I need to differentiate dy dx. So I am differentiating with respect to x. I am differentiating dy dx. That is now everything on the left side. On the right side, I am differentiating negative x, which will just give me negative 1. Now, notice one thing. I want you guys to look at these two. When I multiply this, what do I get? And when I write this, what do I get? Can you guys observe the difference? You see the difference between those two expressions? One gives you the second derivative. The other gives you the first derivative twice. Do you see that? Here, you're multiplying the first derivative times the first derivative. Because of that, this will be the first derivative coming twice. So the first derivative squared. Plus, this side, you have y. But now you're differentiating the first derivative. You're differentiating it again. So for this one, you will have y multiplying the second derivative. This is what we equals to negative 1. Very important, see the difference there. Here, getting the derivative of the first derivative. Here, you are multiplying the first derivative with the first derivative. So you're going to get the first derivative being squared. So to find the second derivative, we'll leave the second derivative alone on the left side. So this will be negative 1, then minus the second derivative squared. The first derivative squared, I mean. Then from here, divide both sides by y. So now you have this squared equal to negative 1 minus the first derivative squared, but divided by y. But when you reach this part, before we proceed, are you guys okay with what we did here? Any questions?
That was quite a lot, but I think I'll catch up with the recording.
Okay. So when you reach this part, it's done. Basically, it's done. But you always end up with a part where you still have dy dx. So this will happen every time when you're using implicit, and then you have to get the second or the third derivative. You always have somewhere in your expression where you have the first derivative. You have already made the second derivative the subject of the formula, but you observe that on the right side, you have the first derivative present. How do you sort it out? Well, you did find the first derivative earlier, and the first derivative was equal to this. So what do? where you have the first derivative, you will put x over y. So where you have the first derivative, you will substitute what you found for the first derivative. So I'll come back to this and say that, hey, I do see my first derivative present. So where I have my first derivative, I'll put what my first derivative is, x over y. What do I get now? So because I'm squaring there, this will be minus. The negative will be squared out. So now I just have x squared over y squared. And then this is over y. Now I want to just write this as a single fraction. So far it's messy. By the way, we're done with differentiating. We're just polishing now. So presenting this in a different way, just trying to polish up, this will be negative y squared minus x squared over y squared. That's just the numerator. In the denominator, we still have this y here. So that finally, we see that this is minus y squared minus x squared over y squared multiplying 1 over y. So that when you multiply, now you will see that this will just be y to the power 3. So this becomes the second derivative. So basically, this is how we do it. It's a little bit messy, but this is how it goes. What I wanted to just highlight the most is how we handle the first derivative when it shows up in a second derivative. We basically just substitute what the first derivative was when we found it. As you might expect, if you had to find the third derivative, there is a high chance that a first derivative will show up on the right side. Maybe even a second derivative might show up on the right side. Should you ever have such scenario, again, just go back to the first derivative you found, go back to the second derivative that you found, and substitute them where they have to be. I think we've done a lot for tonight.